together. Okay, so let's look at the homework. So again, I put it here. And so I only gave you all 4. And I didn't do these before I gave them to you. So I would have liked one of them to at least have a 0 remainder, but it didn't work out that way. Okay. You know, we've had enough practice with that, so it's not a big deal. But I'm just saying that's what if I would have wanted, I would have wanted that to happen at least once. I just didn't want to give you guys a lot of homework. Okay, so you know, here kind of similar to what we just did, and you can factor these two, so you don't need to use the synthetic division table. So you can get all the roots or zeros or x-intercepts. Those are the same thing. Roots, zeros, x-intercepts. Those refer to the same thing. So notice when you get an x squared plus 1, that means you're going to take the square root of -1. And, you know, I'm assuming you know this, but, you know, we represent square roots of negatives with an I, just because it's an easier symbol, and instead of having to drag the square root symbol with a negative all the time. So that's why I put I here, because that means the square root of -1. And the same thing with 71. This is, you could do 4-term factoring, right? So notice adjacent coefficients, 1, 1, -1, -1. Right, and then when you factor this all out, you got a difference of cubes. And when you do the difference of cubes, we had to get the imaginary roots. So instead of saying there's no solution with x squared plus x plus 1, which is true, that's never equal to 0, we have to actually do that. So I went ahead and did the quadratic formula. And so I found the square root of -3. So I just put I in front. And so that's why I'm writing it this way. You put the I in front of the root 3, indicating that it was originally the square root of -3. Okay, just easier, because, you know, you might lose track of that negative if you do square root of -3. So we put the I there, it makes it more manageable. Okay, and then these two, you know, finding the rational roots, I'm not sure that there's probably some wide range of how you guys went about this. You know, so there were a lot of options. So what I did is I did the synthetic division table, just like we did. And I took advantage of the upper and lower bound, which means why go to the next number, because there's no more roots after that. There's no more zeros. Okay, so the rational roots, the factors of the constant term, 12, over the factors of the leading term coefficient, 3. And so here are those. And so you just divide each of them by 1, and then when you divide each of them by 3, sometimes you get repeats. So I didn't write 3 over 3, 6 over 3, and 12 over 3, because we already had those when we divided by 1. Okay, so now that's helpful, okay, but that's a whole lot of numbers. You know, what, 6 times 2, 3 times 2, that's a whole lot of stuff. So doing this just to get a sense of what might work might be worth it. So again, I just stopped if it became a very big positive or negative number, because we don't really care about the value. We just need to know where we go from a positive to a negative. Okay, and then notice when I'm doing the negative, what do you want me to go over on 71? I'm factoring it out. I got the zeros, -1 and 1. And then when you put x squared plus x plus 1 as equal to 0, right, you get the square roots of -3. And so that's why I have that here. That's so I need a little more detail. You know, it's too vague for me to address, you know, when it's a big, wide open question. You know, be more specific. Got it. Got it. Okay, thank you. Again, I really appreciate you guys when you let me know. I'm not offended. All right. All right. So anyway, so notice that when on the negative side, already we're getting alternation. +3, -6, positive 17, -63, positive. So there's no roots less than -3. And that happened again for -2. Okay. And then when we did -1, we wound up with a 0. So that's not a positive or negative, but we went from 8 to negative. So we know there's a 0 between -2 and -1. And again, the same thing. Notice after 2, I stopped. Okay? And that's because, notice, once you did the 2 divisor, you get positive, 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 positive. So there's no point in going to 3. Once you get this on the synthetic division table on the positive divisor side, if they're all positive or all negative, there's no more roots after that. If you're on the negative divisor side, the signs have to alternate. So that's helpful because we don't know anything about this. Between -3 and 2, we already see there's 2 zeros. But look at the degree of this polynomial, it's 4. So we might think, oh, there's 2 more. Okay, so let me keep going. Let me go to 3, let me go to 4, let me go to 5, because you think there's 2 more. But the upper and lower bounds are telling us those 2 more might be imaginary. That's what that's telling us. Okay? Now, the next thing would be these 2 zeros that we see, those 2 zeros are in between -1 and 2 or 1 and 2. So think, oh, wait, okay. Which one of these rational roots is in between 1 and 2? Oh, 4/3. All right, so maybe 4/3 and -4/3 work. Now, usually if one of them works, then the other works too. All right, that's my experience. So I tried that down here and nope, we didn't get a 0 remainder. So those 2 that we see have to be irrational. They have to come from a root. And the only thing we know is where they're located. And so the other 2 are imaginary. Now, the other 2 are very, very highly likely to be imaginary, but there are occasions when these are weird, and sometimes they might do quick loopies between 2 integers. That's rare, but I have seen it. I think I pointed that out on a particular problem earlier. So just to show you what this looks like, you can see if we graph that, that confirms that there were only 2 roots and they're not rational numbers, and those are estimations. You know, but decimals will give you that. Okay, and then number 75, same kind of thing. So here the rational roots, to get what they could be, if they work, would be factors of 1 and factors of 4. So factors of the constant term over the factors of the leading term, so the 1 over the 1, 2, 4. So just divide the 1 by 1, 1 by 2, 1 by 4, and it could either be positive or negative. So we only got like 6. So in this case, it might be worth it just to put them in and see. There's only 6 of them. But I just went ahead and did the synthetic division table. Okay, and notice as you're doing that, all the negatives wind up being lower bounds, all the way to 0. That might mean there's no negative roots at all. And then between 0 and 1, we wound up going from a negative to a positive. So it looks like we've got a 0 in there. And then once I got to 1, I noticed, well, wait, with the 1 divisor, the results are always positive. So that's got to be an upper bound. See how helpful that is? We now know the interval where, if we're going to get roots, where they are. And we only see 1. Well, wait, this was degree 5. So we would have expected 5. So where's the other 4? More than likely, they're imaginary. All right. So the 1 root we see is in between 0 and 1. Well, let's see. Oh, wait. We have a half that's possible, and we have a 1/4 that's possible. All right, let's try that. Let's see if a half works, because that is in between 0 and 1, and that is one of the possible rational roots. And they don't work. Okay, so that means whatever root that is between 0 and 1, it's irrational. It comes from a root of something. It might be a 5th root of something. It might be a cube root of something. It's hard to say because these things can get complicated. We really can't factor this unless we have a 0 remainder. So lucky us, we live in the modern world. And in the modern world, Desmos enables us to just go ahead, type that in there, bada bing, bada boom. Ooh, look at that. And indeed, in between 0 and 1 is the 1 root. All right. really cool. And you guys see this stuff below. That's me setting up when we get to the rational function. So that way, you know, I don't have to take extra time. We can quickly jump on that. All right. Okie dokie. So there's no way you could find the imaginary roots because we don't know how to factor that. Now, we do have a root, but anyway, there you go.